fees. It's a flat rate, $5.2 million per year. All of the other scenarios that are presented there are small modular reactors, the ones that are conceptually being generated. So it ranges from 4 to 30%. As soon as you get over about 5%, it very quickly becomes economically non-viable. It's a non-starter. More importantly, this goes directly against one of the objectives of the NRC, which is to have transparency and a level playing field across all power-producing systems that they're regulating. And so when we started to look at this, they have a proposed sliding scale regulatory fee structure, which is the vertical line. Well, the yellow bars represent existing large reactors. So there's a large fraction of large reactors that now are paying $5.2 million per year in regulatory fees, whereas similar small modular reactors can be paying significantly less than that. So again, this is going against their transparency and their levelized playing field across all reactors. And through a lot of painstaking modeling work, we came up with a better regulatory fee structure, which is a linear fee structure. It takes into a lot of different variables in terms of satisfying NRC needs. And more importantly, what this linear fee structure does is it dramatically changes the landscape. And so it changes regulatory fees across the entire sector to range from 1.2 to 1.6%. Now this does slightly increase regulatory fees for some large reactors from 0.8 to 1.2%. But other large reactors are operating at 2% regulatory fees, so it's expected that this is not going to run them out of business, for example. But more importantly, the fee structure we're proposing to the NRC is directly in line with something that they have as a mission, which is to reward power plant efficiency. So power plant efficiency is on the horizontal axis. On the vertical axis is the percent fees of annual profits being paid in regulatory fees. This is what it looks like now. The white dots are large reactors. The black dots are proposed small modular reactors. This is what it looks like underneath the regulatory fee structure we're proposing. And so it's not perfectly linear based on some capacity factor into the equation here. But again, reactors are being directly rewarded for improved efficiency in the operation of their plants, and it's decreasing and levelizing the playing field. So in terms of our future work in this area, there's a need to expand the work to include environmental impact assessment, not just on operation, but including the construction of the facilities. Specifically looking at grid impacts, economic as well as reliability, understanding the potential of the technology. Very interested in looking at hybrid systems, pushing forward not just in the energy sector, but also in manufacturing. And there's, in terms of funding mechanisms, the Department of Energy is the one that we're targeting right now, directly going through Idaho National Lab through the collaborations that I have up there. Currently, this work's funded through the NRC. We feel like that we've under-promised and over-delivered, and there's an opportunity there to get an extension and continue this work based on the regulatory fee work we're doing. So I'll just have a couple of brief slides on the other technologies. This is water desalinization. This is directly working with collaborators in Jordan to understand direct coupling of photovoltaics with water desalinization systems. So there's no large battery backup system. Technologies move forward where this looks like to be a viable option. So this was integrating all of these tool sets, not just being able to model the actual system, but to be able to model multiple components, perform an optimization that's based on hourly geographical data, coupling with resource availability in terms of water depth, salinity, and the crops that you're actually producing in those systems. So this was really tying a lot of this, the work together, and it was really kind of a neat project. Also wanted to just briefly talk about the yeast biosystems. A lot of information on this. The far left-hand side, again, is this schematic laboratory work feeding into system modeling to then do the sustainability assessment. So in terms of the economic results, this was focused on the production of a biodiesel from integrating dairy effluent or waste with yeast production. So about $4.50 a gallon. That was competitive, I don't know, 2
years ago.
Yeah, 2 years ago, maybe even 6 months ago. $1.60 at the pump is what I saw here. That's really great. On the negative side of things, it's a very large greenhouse gas, primarily due to the fermentation process. So this is not going to meet the renewable fuel standards, but it's a way to upgrade a very low-valued dairy waste product. And then lastly, spider silk systems. Again here, we're doing a lot of process modeling in Aspen to directly inform and understand the cost associated with the production of fibers, providing that data feedback to the experimentalists to say, hey, listen, this is a non-starter. You need to move away from a traditional media and go to a minimal media recipe, for example, in order for this to be economically viable. if you're looking at a carbon fiber precursor, for example. If you're going to be doing, flak jackets for the military, then obviously you can pretty much do whatever you want. So kind of in conclusion, to kind of wrap this up again, talking about this system modeling, one of the things that I think is exciting is that as you integrate this with experimental systems and then leverage that for sustainability modeling, this is applicable to a wide variety of technologies, and it's something that I've really enjoyed. In terms of, in general, my future directions, it's a very dynamic tool set. I've been able to apply it to a wide ranging, it's been primarily focused on energy, but stepped out into some other sectors. There's a lot of value in the data feedback to the experimental systems. Decreasing the resources that are required to move forward in that is very promising. I'm constantly looking for new technologies to explore and understand, and it's a great learning opportunity. The last thing on the research side of things is I've been asked to talk a little bit about grantsmanship. I see grantsmanship in terms of this job, and a lot of you already know this as a critical tool set, and you cannot be successful without it. I typically write between 8 to 12 proposals per year. I've had 10 over the past 4 years successful. I do a lot of things to try to be strategic in the way that I develop those proposals, such that they'll be successful. Those include directly traveling to Washington to talk to program officers, for example, meeting up with program officers at conferences and understanding where the gaps are in their portfolios and who the players are. Strategic collaborations, for example, I think are critically important to be successful on those. Not just understanding who the players are, but who the leads are, and being able to directly work with them. And I think that my best asset is again, being able to deliver on things that I say I'm going to deliver on. And so pressing people through proposal developments means that you be on the next proposal and eventually those get funded. But it is, you can have the best idea in the world, and if you can't articulate that through a well-written proposal, it's a very small chance of getting funded. So that's a general summary of the research and grantsmanship. I'll take the last 10 minutes or so to talk about my teaching interests and philosophy. So dramatically changing gears here. I see a lot of challenges, and I'll talk a little bit in detail about these 3 core topics in terms of teaching. In terms of challenges, technology is continuing to, there's technologies coming on board. It's enabling us to do a lot of things, and it's a good thing because when you look at engines, they've changed a little bit in the past couple hundred years. It used to be I could take it apart and put it back together, and now I, can't even take the plastic parts off the top. No longer is it purely mechanical. There's hundreds of control systems that are integrated into these engines, and so it is truly a multidisciplinary challenge moving forward. There's a need to retain students, increase diversity. There's a lot of advantages associated with these, and so these are some of the challenges I see the engineering profession facing as a whole. When I look at the engineer of tomorrow, the cartoon in the bottom is from Office Space, of course. This guy's sole job is to integrate customers and engineers. This is a non-starter. This job doesn't even exist anymore, right? Is that what I like to tell people is that you either learn to read and write and communicate, or you're going to work for somebody who does. It's a critical component, and really what we're needing to come out of an engineering education with is not just the technical competence, but all of these other skills that are critically important. And I see that see those as important for students to walk out of here with, to be successful and be able to go to where they want to go. And so the question is, how do we do that? And so in terms of getting new students in, what I like to tell people is that there's this misnomer that doctors are the ones that are out there saving lives. Well, without engineers, doctors couldn't do what they do, right? We're generating the tools that enable them to do what they do, and there's this misnomer. We're creating things. We're the ones that are going to push forward and solve problems like global warming. It's going to be a critical component moving forward. And getting students the hands-on experience that they need and bringing in real-world examples, I think, are critically important for getting students engaged and excited about what engineering is. And so examples of how I do this, in my thermodynamics class, I teach a very large undergraduate class, so there's a lot of challenges associated with this, but I bring these design challenges in. So this is one I really like. And so you can go to this website if you've got phones or whatever. It's called freepower.co.uk. So you present that to students, you present that to anybody, and they're like, this is a non-starter for me. It's in the name. And so I tell them, like, you've just been hired, and your boss comes to you and says, we've got this diesel generator that runs all the time. I want to use the waste heat in this organic ranking cycle they tell me, you know, this is going to be great, should I buy this? And I just ask that. And everybody pulls out their phones, and very quickly you can pull up all of these specs that are associated with it in terms of cooling and heating and the efficiency. And through thermodynamics, there's 4 different ways you can evaluate this system, and it turns out every single way it works. It doesn't violate any first laws. It doesn't violate the second law of thermodynamics. And so it's one of those things that's exciting to see students, all the hands go up, I'm not buying this, to the end asking, why aren't you going to buy it? And when they come forward, they're like, I can't come up with a reason other than the name is freepower.co.uk. And then I don't want to buy this, right? And so it's really fun. You know, I'm grateful for this company. I do a lot of demonstrations in class. You know, a lot of you have seen the Drinking Bird, for example, or Stirling engines. One that I've developed is looking at specific heats, and so these are 3 different metals. I've strategically constructed them so they're the same surface area, and they're the same mass, and I make the students figure out all of these things. I give them diameters, and then we heat them up in boiling water, and we predict which one's going to melt through the wax first. And so this is application of the first law through specific heat. Incompressible assumption, constant specific heats. It's really reinforcing all of those. And you know, the students that get engaged, they really dig it. They all come up afterwards and they're like, can we do it again? Let's do it again. And so you know, I end up putting a bunch of wax in the carpet, but it comes up pretty easy. But the students really respond to that. So in terms of my teaching experience, I've taught just over 1,000 total student credit hours, not including this semester. I've taught everything from large undergraduate class to very small graduate level courses. And so at the senior technical level, I teach a renewable energy system class I really enjoy. I really enjoy the senior technical level because students are choosing to be there. And I think that's really exciting. In terms of at CSU, things I'm interested in terms of undergraduate core curriculum, I feel like that if you have a PhD in mechanical engineering, and this is not intending to be arrogant, but you should be able to teach any of the core undergraduate classes. There's a textbook, you can read it. That's usually the difference between your students is you've read the book and they haven't. That being said, I've got a core interest, obviously, in thermodynamics, fluid, heat, mass transfer, energy. Those are the areas that I get really excited about, but I would feel comfortable teaching a variety of other classes, and I've tried to list those there. At the senior technical level, I see that there's a lot of economic classes that have already been developed. But environmental impact is something that I think students, even at the undergraduate level, walking out with environmental assessment tools can be, differentiate them. And ultimately, that's what we're trying to do, is enabling them to differentiate themselves from their peers. And so being able to walk in and be like, yeah, I can perform a life cycle assessment on this engineering production process. I think that's a lot of value. At the graduate level, I'm interested in system modeling for advanced life cycle assessment, and so that's a very broad topic. There's a lot of things that feed into that. But again, here, the core expertise in life cycle. I think the techno-economics is pretty well covered in the established classes that are already here at Utah State, but those are areas, or at Colorado State, those are obviously areas I'd be interested in continuing to work in as well. So with that, I'm grateful for your attention, and I can take any questions. Thank you.
I'm just kind of wondering, in some of your modeling, how you handle uncertainty. And you've got a lot of complexity in there, but then the pieces have some error bars all over the place. I can kind of see how that would fit in with your analysis then.
Sure. So one of the techniques and tools we use is sensitivity analysis, and then integrate that into a statistical analysis to understand, based on T ratios, what variables are sensitive. And so, more importantly, we only have so much resource, right? So for modeling work, you only have so much time, for example. And so one of the important things, and the way that I do this to start, is establish a baseline model, right? And now let's pick what we need to know at a high level of fidelity, what we need to improve. And so through that sensitivity analysis, you can understand, here's an input that we threw in there, okay? Well, it turns out it's very sensitive. And any error in this is going to statistically impact our overall results. And you can perform that sensitivity analysis on whatever metric you want, whether it be greenhouse gas emissions, economic viability, water consumption, for example. And so then you can use those results to go back in and visit and understand and improve the fidelity of the modeling work on that specific aspect. Concurrently, what you can start talking about, and that's where the different, optimistic, baseline, conservative, there are things that you know with a high level of certainty, for example, because you can do them in the laboratory. And so that really represents, hey, listen, it doesn't get worse than this, because I can go do this, okay? And so then as you start going up in terms of those other process scenarios, that uncertainty does increase, and that's what's intended to be represented by, we're bounding the problem, okay?
Sure.
It doesn't get worse than this. And if we do if we can take what we've done in the lab and scale it, which we know we can't, let's just say that we can, we have some advancements, then we've bounded the problem, and this is where we think we are today. Does that answer your question?
Yes.
Okay.
Thank you.
Yeah, John?
Following up on Alan's question, since he asked the one I wanted to ask, can you run your models in a Monte Carlo framework?
You can, so that's not an area that I've done much work in, to be completely honest with you. We're starting to move into that area a little bit. We're starting to do kind of some stochastic modeling in terms of variable changing based on, and it's really driven towards economics, right? And so there's the biggest uncertainty in economics is the future. And so, fuel prices is a great example. And so by using historical stuff, we can start to do some stochastic modeling, integrating those stuff in, but it's really on the economic side of things that I'm just starting to work in that area, but it's not something that I have a huge expertise in. But it does represent a tool set we're looking to explore.
Well, yeah, I mean, I think from the standpoint of Alan's question, it's one thing to say here's the top and the bottom, but the decision maker really wants to know where my probability distribution lies. And so
Yep.
Carlo could probably give you that to a better degree.
Yep, and that's something that we're starting to dabble in that area based on the needs that you guys that you're talking about. So it's really being driven by the alternative technologies that I'm starting to explore and move into. Yeah, Anthony.
How about on the policy? So the nuclear work you're doing is kind of interesting, and it seems like it could really impact policy. So have you kind of delved into that? I mean, it's funded by the NRC, which is interesting, but it seems like there's
It is, right?
next component of whether it's lobbying elected officials or, I mean, what?
Yeah, so it's funny. So what's really interesting about that is that I actually have an undergraduate student who's working on that project, and he's done better work than some graduate students I've had, and it's been great to work with him. And so it's exciting because he comes in and he had an email and he printed it, and I didn't even know you could do that, right? So he comes in and he hands it to me and he goes, "Does this say what I think it says?" And it was an acceptance for a conference talk at the annual ANS. And I said, "Yeah, you have a talk." He's like, "Well, you're going to give it, right?" I'm like, "No, this is your work. You're going to do this. It's going to be great." And so that was the first time we vetted that work. And what was interesting was there were about 10 NRC people that walked in when our talk started and walked out when our talk ended. And so based on that vetting of that work, we were invited up to Idaho National Lab as a seminar speaker, gave that talk there. 2 DOE people were there, and next week we're going to have a call with the program officer back in Washington to continue to expand this work. So they're very interested in kind of what we're doing and the results that we're generating. In terms of next step on the policy, we're trying to get directly in front of the NRC folks and say, "Hey, listen, this is where we're at, this is what we think you guys should be doing." So those are the next steps for us, is to directly get in front of them. So the NRC that's funding it, it's a faculty development grant. So in essence, we can, I have a student who's funded, that's what I get, and I can work on whatever I want, as long as it's related to nuke, whether it be anything. And so this was an area that I saw opportunity in, specifically based on the lack of fidelity in the modeling, and more importantly, that there's going to be this need for power to move forward. This represents unique technology. So there's a lot of unknowns in terms of where that might go. As I told Ben, who's the student, what I want it to be called is the Ben regulatory fee structure, right? So where we're going to try that. Yes, Sue.
With regard to the nuclear stuff in your model, when you were talking about the fee structure and going to a linear structure, I realized your y-axis there was percent of their profit, but it gave me the impression that overall NRC is going to get a lot less fees under your structure.
So the way we do it, right, is that right now they have a flat rate of 5.2 million.
Yeah.
That's it. And so the only money they make, right, money they bring in on regulatory fees is based on large reactors. And so as we started to look at the linear fee structure that we had, there were 2 things we were looking at. One is we need to make sure from the large reactors they're getting the same amount of money. And so some reactors, when you look at that, it does go up a little bit because it goes above that 5.3, and some reactors it goes down. So the slope of that line is dictated right now based on the amount of money that comes in. And so then if you notice too, and so I can go back to it, that at the bottom of the curve, it was actually higher than their proposed sliding scale.
Okay, yeah.
And so in some areas it's lower, In some areas, it's higher.
Right,
And
but
so,
overall,
but overall, the way it's built right now, it'll actually bring in more, it'll bring in the same amount of money, it'll bring in some areas more and some areas less.
right,
And you could alter that slope slightly depending on the size or that you expect the reactor system to be constructed. If you like, well, we expect it to be more in this range, so we want
Right.
to bump it up a little bit, and less at the 45 megawatt range, for
Right.
example.
okay.
To me, the really interesting part of the regulatory piece is the bottom end, right?
Mhm.
Let's see, I mean, there has to be a certain cost to come out and say hi, right?
Right.
And so, to me, that's where it's really interesting, and if that ever starts to become viable, I don't expect it in the near-term future, but in the long term, to me, that's where there's a lot of interesting opportunity for regulatory fees.
Cool. I have one more question. What is the time value of carbon?
Yeah, so this is out there, right? So I don't, so as I start to move forward in my, research career, you kind of say, oh, gosh, I should try to tackle some of these big problems, right? Let's think big and broad, right? So the idea behind this, and this is just one of those things, I have no idea where this is going to go, right? But you can start talking about, whether you believe in climate change or global warming, whatever you want to talk about there, is that, carbon's having an impact, and it's having a financial impact, for example. And so what does it mean to emit a ton of carbon today versus a ton of carbon 5 years from now? And so can you quantify that? Can you put a dollar value on that? Can you put an environmental incentive on that? And so right now, carbon's isn't even valued, right? So Australia played with some things and kind of has pulled back, with taxing dirty people. But again, can you come up with this sustainability model that says, gosh, if you can delay carbon emissions that impacts it this way because technology, I don't really have a good idea, but it's kind of this out there idea of let's put some numbers on this. Let's try to.
It's like if we ever got to a carbon marketplace, that bringing that time factor in would be better.
For sure, that's definitely the long-term vision, right? That if we get to that, that's a long ways out, I think, in having a carbon economy.
Right.
The carbon futures market.
There you go, right? So now all of a sudden, that's, it becomes pretty transparent at that point because you've got a cost for that. But right now, it's how do you quantify carbon emissions with natural disasters or something like that. I don't know, it's a little far-fetched, but something I'm thinking about as I walk to work or something.
Yeah, right.
So I got one good question.
Go for it.
Or,
So, most of the work that you've done over the last 8 years, it's more bad news after another with regards to algae. So I mean, a lot of your work says, oh man, we haven't thought of this, and then we think of it, and the news gets worse and worse and worse. Has anything that you've uncovered over the last 10 years been, oh, well, makes algae look a little bit better? But, I mean, it's a loaded question, because
Notice he's moving to nukes.
No, so I think it's a good question, and so, I think a lot of the research that I do in terms of growth systems has really highlighted, the fact that there is a platform that's robust, and so currently it's expensive, we need to overcome that, but, that's a significant challenge, and any of the open raceway ponds that are being operated, those are almost non-starters because of culture crashes, right? And so I think that some of the growth work that I've done there, and then more recently, some of the integration with produced water, we're starting to actually see some promising results. With some of the heavy metals work, we're doing a freshwater species now, and at some concentrations, we see some, promising, increases in lipid productivity because it represents a stressor. And so there's been some small victories along the way in terms of saying, gosh, integrating with this actually might positively impact the overall productivity. And so on the growth side of things, there's been a couple of small things. When you look at myself, and this just goes back to kind of the vision stuff, is that, my job, in my opinion, is to look at the system and pick areas that people aren't thinking about and go get money to go think about those things. And so, otherwise, there's too many players, right, that are specifically looking at it.
Yeah, well, I mean, the flue gas is a great example. Everybody's been talking about using flue gas, and you've got the heavy metals is a good example.
So there's an example where so Nanoclopsis salina was what we did that. Senodesmus is the freshwater species we're using, and there's actually a dose response curve. You see an uptick at 1x. instead of just the downtick that you see with Nanosalina. And so it's one of those things, now all of a sudden it's species dependent, right? So there's another 3 years of funding. We'll do 4 more species or something like that, right? So, but no, I mean, if it was easy, it would already be done, is what I like to say. So I don't have a good answer for that. Yeah.
Right.
Thanks.
Thank you.